Hi, this is Jacob Mays from SPSS and today I'm going to demonstrate how to select the correct statistical test for exploring relationships and for predicting outcomes. All right. Now, this is part 2 of a 2-part series on selecting the correct statistical test. In part 1, we covered procedures for examining significant differences. So all the tests associated with determining if there are significant differences between groups and time periods were covered in video 1. And here we have the test selection matrix, which will help you select the correct statistical test. So if you would like video 1, just leave a comment in the comment section and I will send you video 1. Now, if you would like the test selection matrix that covers both statistical tests for examining significant differences and relationships, just type in interested in the comments or just send me a messenger, a DM inside Messenger. All right. All right. So I'm Jacob Mays. I'm the founder of SPSSvideotutor.com. I have been engaged in statistics at the advanced level for about 30 years now. I was a former head of research, the B2B division at Office Depot, and this is what I do full time. I help dissertation students and academicians analyze their data for their studies. All right, so test selection matrix, procedures for exploring relationships and prediction. All right, so the first test that we're going to cover is the bivariate correlation, okay? And this is used when you want to assess the linear relationship between two variables. Specifically, this test provides information on the strength and direction of the relationship. Okay. Now, here's what you need to run this test. You need 2 continuous variables or 1 continuous variable and 1 dichotomous variable. So dichotomous means you have a variable that has only 2 options. Dichotomous, 2 options. So male and female, 0, 1. Okay. But they have to be coded using numbers. All right. Now, with the bivariate correlation, there is no independent or dependent variable, okay? Because independent variable means that there's a variable affecting another variable, the dependent variable, okay? With the bivariate correlation, there is a mutual impact, okay? There is no one variable affecting another variable. The impact is mutual. Okay. So we don't say that there's an independent or dependent variable because the relationship is bidirectional. All right. So that's very important. So let's say, for example, we wanted to look at the relationship between height and shoe size. Right. So essentially what you would have is you would have data where you'd have height and then shoe size for each respondent. So this is respondent 1, respondent 2, respondent 3, and so on and so forth. So this person may be 72 inches and they may have a size 10. This person may be 65 inches and they have a size 8. And this person may have 60 inches and they have a size 7. Okay. And you probably want to have gender on here too, but essentially you would look at the relationship between these variables. And essentially what you would have here is when you would plot them. So you'd have, let's see, shoe size and then height. Okay. So height, we would be, let's see, this would be 7, 8, 9, and 10. And then, oh, I'm sorry, that's height. So we're going to call this shoe size and we're going to call this one height. All right. And then height, we're going to say 60, 65, 70, 75. So, okay, so 72 would be over here, and then 72 and a size 10 would be here, and then we've got 65 and a size 8, that would be here, and then 60 and a size 7, that would be here. And you see that there's a linear relationship, okay? Positive linear relationship. So that's bivariate correlation when you want to look at the linear relationships between variables, all right? All right, next, we have the bivariate linear regression. Now, this is different. It's very similar to the correlation, but this implies that one variable is affecting or is used to predict another. Okay, that's the difference between the regression and the correlation. The correlation assumes that there's no variable affecting another, that there is a mutual or bidirectional relationship. Regression assumes that one variable is impacting, not causing, but is impacting another. Okay, so for example, this procedure tells us how well one independent or predictor variable predicts the dependent or outcome variable. So you need one predictor variable that is continuous or dichotomous, right? Dichotomous means it has a one or two option. It has only two options. And then the dependent variable has to be continuous. It has to be measured on an interval or ratio scale. Okay. All right. Next, we've got the multiple linear regression. So for the bivariate linear regression, let's say we're trying to see if IQ influences GPA. Okay. Right. We wouldn't expect GPA to influence IQ. We would expect theoretically IQ to impact GPA. So IQ would be the predictor and GPA would be the outcome variable. Okay. Because this is one direction. It's not bidirectional. It's unidirectional. We expect this to impact that. Okay. All right. Now, multiple linear regression. Okay. So here you would have multiple predictor variables. Here we have one predictor variables. Here you have two or more. So let's say we're trying to predict GPA. Okay. So we have IQ as one variable, but then as another variable, we have hours studying. Right. So that might be another variable that predicts. Okay. So that we would use a multiple linear regression because we have two predictor variables. A bivariate linear regression is only when you have one predictor variable and one outcome variable. Here we have two or more predictor variables and one outcome variable. So that's when we would use a multiple linear regression. All right. Now, and again, this has to be continuous. All right. Now, a binomial logistic regression is another type of regression, but the outcome variable, instead of being continuous, is categorical. So this is used to assess how well two or more independent predictor variables predict a categorical dependent or outcome variable. Okay. That is dichotomous. That only has two options. All right. So let's say, for example, we're trying to predict whether or not someone gets sick or catches a cold in the wintertime, right? So the outcome variable would be catch a cold, right? And that would be yes or no, right? So that's the outcome variable. And let's say we're trying to determine if vitamin C consumption is a predictor of whether or not someone catches a cold. Okay. So vitamin C. Let's also use, let's use outdoor temperature. We'll say temperature, outdoor temperature, the average temperature outdoors or daily temperature, right? So that might be used to predict whether or not someone catches a cold. So this is dichotomous, yes or no. And these are your two predictor variables. Vitamin C consumption, you know, do you have high vitamin C consumption, medium vitamin C consumption, low vitamin C consumption? And then what is the temperature outside, okay, across a specific time period, all right? So this is what we would use for a binomial logistic regression. Now, for a multinomial logistic regression, we have a situation where your outcome variable has 3 or more categories, okay? Used to assess how well 2 or more independent predictor variables predict a categorical dependent outcome variable that is not dichotomous or has more than 2 possible outcomes, okay? It has more than 2 possible outcomes. So it's 3 or more outcomes, right? So let's say your outcome is transportation, or the way you commute to work. You may take the bus, you may drive, or you may take the train. Okay. So let's say we're trying to determine. So this is transportation is your outcome variable, transportation to work. And you're trying to predict whether someone takes the bus, whether they drive, or whether they take the train. So you might look at their income. You might look at where they live. Do they live in the city or the suburbs? And then you also might look at, let's see, income, city, or suburbs. That's fine. Okay. So then you would use these two predictor variables to determine if a person takes the bus to work, they drive to work, or they take the train to work. These are 3 possible outcomes. So you would use a multinomial logistic regression where you have 3 or more outcomes that are possible. All right. All right. And then we have what we call a factor analysis. Okay. Factor analysis is used when you want to reduce data into smaller chunks, right? So let's say, for example, you have a questionnaire, okay? And you have 10 questions. You have 10 questions, right? And you want to see, do these questions form any kind? Now, they have to be all measured on the same scale. Measured on same scale. So they're either 1 to 5 Likert or 1 to 7 Likert or strongly agree, disagree. They all have to be measured on the same scale. That's very important. And then you're going to see, okay, are any of these questions correlated such that they form a concept, right? So do the first 3 form together to form a concept? Do the next 2 work together to form a concept? And do these form a concept? So that's what you're doing with a factor. You're trying to determine, it's a data reduction technique. So in other words, it takes a large group of data and it says, okay, are these questions related to one another so that I can form smaller groups? Okay. Factor analysis is data reduction technique. It takes a large set of data and reduces it to factors or components by looking at groups among intercorrelations of the set variables. All the variables need to be continuous. That's very important. And they all need to be measured on the same scale. That's all very important. So if it's a 1 to 5 scale, strongly agree versus disagree, likability, the scale has to be the same and the numbers of the scale options have to be the same as well. All right. And then we've got the reliability analysis. Now, reliability analysis is run when you have a scale or you're using an instrument from another study and you want to see if your instrument, that instrument that you're using with your sample, is reliable with your sample. Okay. So you test validity and you test reliability. You would use Cronbach's alpha reliability analysis to determine if your instrument, the instrument you're using from another study, is actually reliable, a reliable instrument with your sample. Okay. Cronbach's alpha is a measure of internal consistency. And so essentially it's asking, is there consistency in the way that people are answering the questions? Are their answers consistent? So anything that's 0.7 or above indicates acceptable consistency in the way they are responding to the questions. And again, you have to have the same scale and they have to be the same anchors. So likability, strongly agree, disagree, same number and same anchors. All right. So anything that's 0.7 or above is considered reliable. It's a reliable scale with your sample. And then finally, we have chi-square. Now, chi-square is a little different because what it does is it looks at the relationships between categorical variables. Okay. So if your variables are categorical, then you would use a chi-square test of independence. So let's say, for example, we wanted to look at, is there a significant association between gender? Oops, too big. Gender, so male and female, and whether or not they say graduation rates. So we'll say 2023 graduation rates. So did they graduate in 2023? Yes versus no. Okay. All right. So that's what we're looking at. And what we're doing is we're comparing to see if there's a relationship and see if there's a difference. So let's say there are 10,000 students, right, at a college. We want to know what percentage of the females graduated. So we'll say 20% graduated, and we'll say 10% graduated, and we'll say 80% and 90%. So essentially what we're trying to determine is if there's a significant difference in the percentage of females that graduated versus males, right? So essentially the chi-square test is done when you want to compare differences between groups, two groups, and you want to compare them because they're categorical and you're looking at the differences in percentages, okay? So that's the chi-square test of independence. Now, if you would like a copy of the test selection matrix, type in interested in the comment box. If you need assistance selecting the test selection for your study, you can type again interested in. I'll reach out to you for the test selection matrix. I'll send it to you via your messenger. Okay. If you have any questions, please post your questions below in the comment section. All right. So this is part 2. If you want part 1, let me know and I will send it to you via messenger. All right. All right. Much success in your data analysis.